In this video, we're going to talk about going the opposite direction of the previous video. That is, we're going to say that this graph in red, is the derivative graph, and we are being asked to draw the original function whose derivative is this red graph. As usual, we're going to go through and identify some of the important elements of this graph so that we know what might be happening to the original graph. So the first thing, as always, is to identify critical points. But since this is the graph of the derivative, we identify critical points by intercepts with the x-axis. So that's going to occur at -2, 0, and 1. Let's mark those values on our number line for f prime. So at x equals -2, we have a 0 derivative, and the same thing at x equals 0 and x equals 1. We can also observe that the derivative is going from negative to the left of x equals 1 to positive to the right of x equals 1. We can do this exact same thing with the other critical points. So at x equals 0, the value of the derivative is going from positive to negative. And at x equals -2, we can see that the value is positive to the left of x equals -2, but it's also positive to the right. So we can then say that the derivative is positive throughout that entire section between x equals -2 and x equals 0. Let's also look at the second derivative. Now the second derivative we're going to be able to tell by looking at the slope of the first derivative graph. Let's start with x equals -2. We can see that to the left of x equals -2, the slope of the graph appears to be negative. To the right of x equals -2, the slope appears to be positive, which means we must have an inflection point right at x equals -2. Now we'll mark this with a 0 so that we know to include that as an inflection point later on. Let's also notice that just to the right of x equals -1, we see another location where the sign of the derivative of f prime of x, that is the second derivative, changes from positive to negative. So there's another location where there could be an inflection point there. We also see a possible inflection point right around 0.6, where the derivative changes from being negative on the left to positive on the right-hand side. One thing that can be really useful before you actually start drawing the graph is drawing a little sketch of what a function looks like in each section of the number line. This is made even better by considering the combination of what the first derivative is doing and the second derivative. Let me show you what I mean. So at this critical value, around x equals -2, we can see that we have both a critical point for the graph of f, because the derivative is 0, but we can also see that it's an inflection point. And it's an inflection point where the concavity is changing from concave down, because the second derivative is negative, to concave up, because the second derivative is positive. That graph, I'm going to make a little sketch of what that looks like. I know then that a graph that has a critical value that coincides with an inflection point is going to look a little bit like this. Let's also look at this next inflection point where the second derivative changes from positive to negative, that is concave up to concave down. But notice we do not have a critical point at that value. We have a point of inflection happening at this x value. We know that it's changing from positive concavity to negative concavity, but we also know that the derivative is positive the entire time. So we need to think about how we draw an inflection point such that the first derivative is positive, but you have an inflection point where the concavity is changing from positive to negative. And so if we think about it, that graph is going to look a little bit like this. We then have a critical point at x equals 0, and we can see that the graph, the first derivative, is changing from positive to negative. And concavity is negative, which means that the graph at this critical point is going to look a little bit like this. We have another concavity change right here, and we can see that the concavity is changing from concave down, because the second derivative is negative, to concave up, because the second derivative is positive on the other side. We also can see that within this region, the first derivative is negative. And so we can think, what does a graph look like when it has an inflection point changing from concave down to concave up, but the derivative is negative? So when you think about it, and that inflection point is going to look a little bit like that. Finally, we know that at x equals 1, we have the derivative changing from negative to positive, which using the first derivative test or the second derivative test tells us that the graph has to somehow look like this. Now from all these teeny little sketches, we can kind of piece together what this is going to look like, because all we now have to do is connect these regions of the graph together. So let's see if we can piece all of this together. So the first thing, let's start on the left-hand side. We can see that we're going to have an inflection point and a critical point right at x equals -2. We then see that at x equals -1, this is where we're going to start to have this other inflection point that's coming from this little graph right here. That is then going to lead to a maximum value at x equals 0. So we can continue drawing it so that the maximum value occurs at x equals 0. The next thing, we know that we have a concavity change from concave down to concave up right around that x equals 0.6. And then we have a minimum value at x equals 1 before that graph then slopes up and goes on from there. Okay, now, your graph may not be exactly the same as mine. It might move up, it might move down, but the general shape should be about the same. So again, this is the complete process for going from a graph of the derivative to a graph of the original function.